There's a slab of black granodiorite sitting behind glass in the British Museum that changed the course of human knowledge, and almost nobody who walks past it realizes how strange its real story is. Not strange in the way internet videos like to claim, with hidden codes and buried warnings. Strange in a quieter, more human way. A story about a lucky accident, one obsessive young scholar, and a document that turned out to be almost boringly ordinary, except that its ordinariness was exactly what made it priceless. This is the true story of the Rosetta Stone, how it was actually deciphered, what it actually says, and how artificial intelligence is genuinely being used today to read ancient texts that humans have never been able to read before. No embellishment needed. The real story is good enough on its own. In the summer of 1799, Napoleon Bonaparte was in the middle of his Egyptian campaign, a military and scientific expedition meant to secure French interests and, not incidentally, to loot as much scholarly prestige as possible from a civilization Europe had only half understood for centuries. French soldiers were reinforcing a crumbling fort near the town of Rashid, known to Europeans as Rosetta, on the Nile Delta. They were not archaeologists. They were laborers, tearing down old walls to build new ones, and somewhere in that rubble a soldier noticed a large, dark stone slab covered in unfamiliar carvings. It was not gold. It was not dramatic. It was just a heavy, broken chunk of rock with writing on it, and if it had been slightly less unusual it might have ended up as building material like everything else around it. But an officer recognized that something was different about this particular stone, and instead of being mortared into a wall, it was set aside. What made it different became clear almost immediately. The stone bore the same inscription written 3 separate times, in 3 different scripts, stacked one above the other. At the top was Egyptian hieroglyphic script, the elaborate pictorial writing found on temple walls and tombs. In the middle was Demotic, a cursive, everyday form of Egyptian writing used for administrative and legal documents. At the bottom was ancient Greek. And Greek, unlike the other 2, had never stopped being readable. Scholars in 1799 could sit down and translate the bottom third of the stone immediately. That single fact was the whole reason the stone became famous. For the first time, there was a document where a known language sat directly beside 2 unknown ones, both of them presumably saying the same thing. It was, in effect, a bilingual dictionary that had been waiting in the ground for 2,000 years. The significance of this cannot be overstated, because before the Rosetta Stone, hieroglyphics were not simply untranslated. They were considered by most European scholars to be fundamentally unreadable as language at all. For centuries, the dominant theory, inherited partly from a mistaken ancient Greek writer named Horapollo, was that hieroglyphs were symbolic or allegorical pictures, not a writing system tied to actual spoken sounds. Under this theory, a picture of an owl did not represent a sound the way a letter does. It represented an abstract idea, a bit of philosophical or religious symbolism that had to be intuited rather than read. This idea persisted for well over 1,000 years and sent generations of scholars down dead ends, because you cannot decode a phonetic alphabet if you insist on treating it as picture symbolism. It's a little like trying to interpret the English alphabet as a series of mystical icons, instead of realizing that B just makes a but sound. Once you assume the wrong category, no amount of cleverness gets you to the right answer. So for centuries, Egyptian temple walls, tomb paintings, obelisks, and monuments stood as a kind of visible but silent record. Historians and antiquarians could see that something was being communicated. Rows of careful, deliberate symbols, clearly organized, clearly meaningful to the people who carved them. But there was no way in. Enthusiasts speculated that the hieroglyphs might be astrological charts, secret religious codes, or purely decorative art with no linguistic content at all. Entire civilizations' worth of history, administration, religion, and daily life sat encoded on stone and papyrus, and nobody alive could read a word of it. The Rosetta Stone did not solve this problem instantly. Its discovery in 1799 sparked excitement, but the actual decipherment took more than 20 years, and it wasn't accomplished by the French. Napoleon's forces surrendered to the British not long after the stone was found, and under the terms of the surrender, the stone was handed over to Britain, arriving in London in 1802, where it has remained in the British Museum since 1802. missing a brief evacuation during the World Wars. But before it left French hands, scholars had already made copies and casts of its inscriptions, which meant that researchers across Europe could work on the puzzle even without the physical object in front of them. Progress was slow and often wrong. An English polymath named Thomas Young made real headway in the early 1810s. Young correctly guessed that some of the hieroglyphic symbols enclosed in oval loops, now known as cartouches, represented royal names. Reasonable assumption, since foreign names would need to be spelled out phonetically rather than represented by ideas the way native Egyptian words might be. Young used this insight to tentatively work out a handful of phonetic signs, including some of the sounds in the name of the Ptolemaic ruler mentioned in the text. It was a genuinely important breakthrough, but Young still held onto the older assumption that most hieroglyphic writing was symbolic rather than phonetic, and his work stalled. The person who actually broke the code was a young French scholar named Jean-François Champollion, and his path to the answer says as much about obsession as it does about genius. Champollion had been fascinated by Egypt since childhood, reportedly declaring as a boy that he intended to be the one to decipher hieroglyphics, and he spent years teaching himself Coptic, the language descended from ancient Egyptian that was still used in Egyptian Christian liturgy. This turned out to be the crucial move, because it gave Champollion a living sense of how ancient Egyptian actually sounded and how its grammar worked, something none of his rivals had. Working from copies of the Rosetta Stone alongside inscriptions from other monuments, Champollion focused on the cartouches, the royal names, just as Young had. He compared the hieroglyphic spelling of the name of Ptolemy, the Greek-descended ruler mentioned on the Rosetta Stone, with the hieroglyphic spelling of Cleopatra, found on a different inscription, the Banks obelisk. Because he could read the Greek versions of both names, Champollion could predict which hieroglyphic symbols ought to represent shared sounds, like the P and O and L that both names contain. When the predicted symbols lined up correctly between the two names, it confirmed that hieroglyphs were, at least in part, a genuinely phonetic script, signs standing for sounds, not just abstract ideas. From there, Champollion expanded rapidly. He realized that Egyptian hieroglyphic writing was a complex, mixed system. Some signs represented sounds, some represented whole words or ideas, and some acted as clarifying markers to indicate how a word should be categorized or read. This was a genuinely sophisticated writing system, not primitive picture symbolism, and once Champollion understood its actual internal logic, previously silent inscriptions across Egypt began to speak. In 1822, he presented his findings to the French Academy in a now famous letter, and within a few years the broader framework for reading hieroglyphics was firmly established. It is worth pausing on how significant this was. An entire civilization's written record, its religious texts, its royal chronicles, its legal documents, its private letters, its poetry, became newly accessible after being locked away for well over 1,000 years. It is one of the great intellectual triumphs in history, and it happened because of patient comparison, linguistic training, and a lot of trial and error, not sudden revelation. So what does the Rosetta Stone actually say? Now that we can read every line of it, the answer, honestly, is a little anticlimactic, and that is part of what makes it interesting. The text is a priestly decree issued in 196 BC, during the reign of the boy king Ptolemy V, one of the Greek-descended pharaohs who ruled Egypt after Alexander the Great's conquest. The decree was passed by a council of Egyptian priests gathered at Memphis, and it is essentially a piece of political and religious housekeeping. It praises Ptolemy V for various acts of generosity toward the temples, donations of grain, tax relief, funding for religious institutions, the release of certain prisoners, and the suppression of a rebellion. In exchange, the priests agree to honor the king with a cult statue in every temple, to establish a festival in his name, and to have this decree itself inscribed on stone and displayed prominently in temples across the country, in all three scripts, so that everyone could understand it. That three-script requirement is actually specified in the decree's own text, and it tells us something genuinely important about how the Ptolemaic government functioned. Hieroglyphic script carried religious and royal authority. It was the language of temples and gods. Demotic was the practical, everyday script of Egyptian administration and daily business, used by scribes and officials. Greek was the language of the ruling class, since the Ptolemaic dynasty was of Macedonian Greek origin, by mandating that the decree appear in all three. The priests and the crown were making sure the message reached every layer of Egyptian society simultaneously: the traditional religious establishment, the native administrative class, and the Greek-speaking governing elite. It wasn't a secret message. It was the opposite of a secret message. It was designed to be as public and as widely understood as possible, carved into durable stone specifically so it couldn't be ignored, forgotten, or altered. That durability is itself worth noting, because it reflects something true about ancient record-keeping generally. Stone doesn't burn like papyrus, and it doesn't rot like wood or cloth. When ancient governments and religious institutions wanted a message to survive, a treaty, a law, a royal decree, a boundary marker, they carve it into stone, precisely because they understood that everything else eventually disappears. The Rosetta Stone is one small, fairly minor example of thousands of similar decrees that would have been produced and displayed throughout the Ptolemaic period. It survived mostly by chance, having been reused as building material centuries later, which is likely part of why it ended up in a fort wall waiting to be found by soldiers looking for stones. Now, understanding what the Rosetta Stone actually is doesn't make the broader story of ancient decipherment any less remarkable. If anything, the real methods used today are more interesting than invented ones because they are things we can actually verify. In the years since Champollion, and especially in the last decade, researchers have increasingly turned to computational tools and artificial intelligence to help with exactly this kind of work: reading damaged, incomplete, or previously undeciphered ancient texts. This is real, published, peer-reviewed research, and it's worth walking through some of it, because it shows what AI can genuinely contribute to archaeology and philology, without needing to invent hidden prophecies to make it compelling. One of the clearest examples comes from ancient Greek epigraphy, the study of inscriptions carved in stone. Researchers at DeepMind, working with historians at the University of Oxford and CA, Foscari University of Venice, built a machine learning system called Ithaca, designed specifically to help restore damaged ancient Greek inscriptions, estimate where and when they were originally written, and suggest plausible missing text where the stone has broken away or worn smooth. Thousands of Greek inscriptions survive only in fragments, and historians have traditionally had to rely on their own trained intuition to guess what's missing, comparing damaged texts to similar surviving ones by hand. Ithaca was trained on a large dataset of Greek inscriptions and learned the statistical patterns of how ancient Greek formulaic language worked, the kinds of phrases that typically appear in decrees, dedications, and epitaphs. In tests, the model was able to help historians restore missing text with meaningfully higher accuracy than they achieved working alone, and interestingly, when historians used the tool as a collaborative aid rather than a replacement, their combined accuracy was higher than either the model or the humans achieved independently. That collaborative pattern, AI proposing candidates, humans applying judgment and context, is probably the most realistic picture of how this technology actually helps with ancient texts, rather than the human versus machine framing that headlines often prefer. A second major area is the Herculaneum papyrus scrolls, a genuinely dramatic story in its own right. In 79 AD, the eruption of Mount Vesuvius that famously buried Pompeii also buried a nearby villa in Herculaneum, carbonizing an entire library of papyrus scrolls in the process. The scrolls survived physically, but they were burned into brittle, blackened cylinders that crumble if you try to unroll them, and for over 2 centuries most attempts to physically open them destroyed the very text people were trying to read. Beginning in the 2010s, researchers began using X-ray micro-CT scanning to image the scrolls without unrolling them at all, capturing their internal structure layer by layer in 3 dimensions. The remaining problem was that the ink used, a carbon-based ink, is nearly invisible to X-rays because it has almost the same density as the carbonized papyrus it sits on. So even with a perfect 3D scan, the writing itself was invisible. This is where machine learning made the crucial difference. Researchers, most notably through a public competition called the Vesuvius Challenge launched in 2023, trained neural networks to detect extremely subtle textural differences in the scanned data that correspond to where ink sits on the papyrus surface, even though the ink itself doesn't show up directly. In 2023 and 2024, teams working on this challenge successfully read substantial passages of previously unreadable text from a carbonized scroll for the first time in the scroll's nearly 2,000-year history.